We are going to illustrate those numerical methods with an example. Let's take a look at the following Cauchy problem. U prime of t equal sine of 1 plus v times sine of t u of t cubed to the third power times u of t, with initial condition u of 0 equal 1. That is a nonlinear, non-autonomous differential equation, and it is sufficiently interesting to be a nice challenge to any numerical solver. On the right-hand side, the cube of the sine function that is multiplied to u of t will occasionally be positive and occasionally be negative. So sometimes u is going to experience something similar to exponential growth, and at other times it's going to experience something akin to exponential decay. Just to have a reference, we use the explicit Euler method with a very tiny step size to get an approximation to the solution of that differential equation. What you're seeing here is a numerical approximation to the solution from time t equals 0 up to t equals 10. This is being computed with 1 million time steps, so we can assume it's sufficiently accurate for our purposes. Let's keep the reference in the picture, just for the sake of comparison. Of course, 1 million time steps are quite lavish. So let's see what happens if we take a bigger time step. What we see here are the results obtained using the explicit Euler method with several much coarser time steps. The blue curve here is still our reference solution. And then we have got, with a step size of 0.5, the orange curve, the green curve with a step size 0.25, and the red curve with a step size of 0.125. Taking a look at this picture, we can tell that the explicit Euler method converges to the true solution as we keep decreasing the step size. Nevertheless, these guys look still far off. Now let's see what happens if instead of the explicit Euler method, I use the explicit midpoint method. For a step size of 0.5, the numerical approximation that I obtain from the explicit midpoint method still looks only so-so, but then as I decrease the step size by 50% with a step size of 1/4, 0.25, the green curve already looks fairly close to the reference solution. And then again, as I decrease the step size by 50% with a step size 1/8, 0.125, it's not easy to distinguish the red curve from the blue curve, our reference solution. Of course, there's still an approximation error, but this looks already quite good. So as I decrease the step size by 50%, the explicit midpoint method pays this back much better than the explicit Euler method. A similar result is also true for Horn's method. The approximation is coarse at best with a step size of 1/2. But then again, with a step size of 1/4, as in the green curve, we already see a fairly nice approximation. And then again, with a step size of 1/8, the red curve is very close to the blue curve, our reference solution. So just as with the explicit midpoint method, Horn's method also delivers fairly good results. Horn's method tends to deliver much better results than the Euler method, than the explicit Euler method, for the same step size. Let's get back to the explicit Euler method for a moment. So as you recall, the explicit midpoint method and also Horn's method are explicit methods, just like explicit Euler, which means that at each iteration step, you can just obtain the next iterate by some straightforward computation. But we've also seen implicit numerical methods, the implicit Euler method, the implicit midpoint method, and the Crank-Nicholson method. Now, instead of the explicit Euler method, let's take a look at the implicit Euler method. The implicit Euler method seems to perform somewhat worse than the explicit Euler method for this particular example. So after some time, the solutions obtained from the implicit Euler method seem to hover above the true solution, but they still converge. So again, I've used the same step sizes. The orange curve is step size 1/2. The green curve is step size 1/4. And the red curve is step size 1/8. The blue curve is still our reference solution. Okay, let's see how the implicit midpoint method performs by comparison. Of course, it performs much better. We still see a very rough approximation for step size 1/2. But as soon as I decrease the step size to 1/4, and even more so as I decrease the step size to 1/8, the curve produced by the implicit midpoint method delivers a very good approximation to our reference solution. So just as with the explicit methods, in comparison to the implicit Euler method, the implicit midpoint method pays back a much better approximation quality for the same step size. And even though the computational effort for each step is a bit larger than for the implicit Euler method, the improvement in approximation completely outweighs this additional cost. Last but not least, the Crank-Nicholson method, which is sort of the implicit cousin of Horn's method. Both methods are based on the trapezoidal rule. And we see, okay, for step size 1/2, the approximation is kind of rough, but for step sizes 1/4 and 1/8, the approximation gets fairly close already to the reference solution. Again, in comparison to the implicit Euler method, with the same step size and only a little bit of additional computation at each approximation step, at each iteration step, we get a much better return of investment in terms of approximation quality. The moral of the story: the theoretical work that we invest in developing these not quite trivial methods pays off in terms of computational performance. We obtain fairly good approximations with fewer computational resources, less energy consumption, and in much shorter computation time.